Welcome to lesson number 39 of the course on industrial automation and control. This is the penultimate lesson, and therefore, while we are ending the course, we need to be aware of at least some of the things that we have not done in detail. In this course, we have mainly talked about the lower levels of automation, namely level 0, where we have talked about sensors and actuators in some detail, and level 1, which is automatic control and sequence control. But as we have discussed, there are higher levels of automation systems. There is level 2, level 3 and conceivably level 4. So, in today's lesson we will try to take a look at it's going to be a brief look, but nevertheless take a look at what makes level 2, 3 and 4, so that we have some idea about them and get a more complete picture. This is about industrial automation, not so much about it turns out that the higher levels are more concerned with information technology and software rather than automation technology and hardware. So, therefore, they have not been treated in detail in this course. So, here we go. So, as usual, instructional objectives and name the higher layers. So, the student should be able to at least name the higher layers and name the major functions of each of the higher layers, level 2, 3 and 4 automation, and describe the many of them. There are basic technologies which are involved in this are monitoring technologies, optimization technologies. Part of it gets manifested in planning and scheduling. So, students should be able to talk about what is process monitoring, how it is done, why it is important. Then planning and scheduling, what is planning and scheduling, and how how in the overall automated factory industrial information technology plays a role in coordinating, integrating these complex operations for squeezing out performance, getting productivity, efficiency to gain an edge of competitiveness in the market. Okay. So, we first take a look at the automation pyramid. Remember, we had taken a look at this automation pyramid in the very early parts of the course. So, here as we said that this is the automation is organized, it can be viewed as a pyramid with the process machine, the basic equipment at which is the ground, and then you have the sensors and actuators which take information and provide control inputs. Then you have the first layer of controls, automatic controls, and in this course we have mostly been concerned about these two layers. We will select thicker pen. So, we have mostly been concerned about these two layers, and in this lesson we will take a look at the higher 3 layers. So, all these layers are basically have different functionality, and obviously, the higher layers take feedback from the lower layers, and they give reference commands or set points or to the lower layers as to what is to be achieved. They set the targets for the lower layers, and therefore, all this information. So, there is information passing back and forth. So, there is a communication system, and we have already learnt about such a industrial communication system. Then there is a spatial time scale difference among the layers. While the sensors and actuators look only at a part of a machine, but look at it in great time resolution. As you go up, the layers of automation at those levels look at much bigger geographical areas. First it talks about unit control, where one piece of equipment is looked at. Then you talk about group level control, where groups of equipment are looked at. Then you can talk about shop level control, you can talk about factory level control, and so on, and finally you can talk about enterprise level control. So, as you go up, your geographical extent goes up, and your time resolution or your time scale also goes up, which means that you don't look at things on minute time scale, but start looking at things in terms of hours to days, days to weeks, sometimes months. So, when you are doing enterprise level planning and optimization, you typically look at months of operation, while if you are looking at automatic control level, then you are typically looking at minutes level or signals at levels of second to minutes, right. So, we see that this is the way complex automation systems are organized, and functionally, typically you will find that level 1 and 0 we have seen there. Levels 2, 1 and 0 actually basically constitute of control systems. So, they talk about physical dynamics, they talk about the physics of the process, heat transfer, mass transfer, signal value. So, they are kind of one kind of technologies. So, they have been clubbed level 2, 1 and 0, they are all control technologies. Beyond that, you have level 3, or sometimes the systems which, or the computing systems which support the performance here and do the kind of computation that are required are called manufacturing execution systems which actually plan production, take a check at resources, track how particular how a particular order is being produced, take care of quality, etc. So, such systems are the manufacturing execution systems. So, they actually basically they are interfaces between the business and the engineering systems. So, they take on one side the interface with the business systems and take orders, production deadlines, etc. And on the other hand, they actually produce, they take these targets from the business systems and they translate them into engineering targets exactly in terms of schedules of production, which machine to be used at what time, and then and once these are now handed down to the supervisory control system, then the supervisory control system can act according to that schedule and actually do execute the steps that are required to do the physical manufacturing, right. So, functionally you can have, if you see the nature of technologies, then you will find that this is one nature of technology which are essentially business systems, enterprise resource planning, etc. On the other hand, these systems are still related to the engineering equipment, but look at them as behaviorally and just model them in terms of their functionality and their some performance parameters, and model the manufacturing process just like a sequence of operations while the actual physical entities are handled at the control system levels. So, this is the way it goes. So, we are going to talk about the supervisory control, manufacturing execution, and to some extent the business systems today. So, if you take a brief look at the various levels. At the highest level, you have enterprise level systems or business systems, where you talk about finances, human resources, you talk about documentation, you talk about long term capacity planning, whether you need to, looking at the order and looking at the market, whether you need to set up a new plant or you need to acquire a certain kind of machine, what kind of production goals you want to achieve, and these are the kind of things that are actually done at the enterprise levels. And we are going to this is just for our awareness. We are not going to be we are not experts on this, and neither are we going to deal with this in a course, but it is good to know that this is what the business system does. It actually finds out, basically it is directly interfaced to the market, and it actually finds out that what should be the kind of production resources and production schedules, so that profit can be made. Below that is level 3. So, once this enterprise level comes out with orders and provides schedules of various, I mean the capacities which are going to be available, then the manufacturing level actually sits down and says, okay, so now I have to make so many pieces of this over such time with such kind of resources, right. So, now how am I going to actually do it? So, when am I going to make what, and how am I going to schedule my machines, and when I am going to maintain what, when I am going to take off a particular machine and then give it for maintenance. So, all this is done at the manufacturing level. So, typically you do a, so once you have done that, then you know the exact production sequence and when what will be produced. So, you have a kind of schedule. Now, you can send this schedule that, okay, now everything is fixed up. So, now you produce, actually physically produce according to this schedule. So, then the supervision level actually takes this and makes the firstly it makes the production, that is it actually finds out the configurations of these machines as they have to be configured for a particular manufacturing, and they actually run these machines according to this, download the configurations and then give the proper commands, such that the machines actually start producing. And they also supervise the overall production process. They actually optimize and deploy control strategies. So, they actually manage the whole production. Sometimes it is done automatically, sometimes it is done manually. So, when it is done, so in many cases it is done manually, that is using operators. So, these systems visualize, give the operator a view of what is happening in the plant. They also store process data for future use. They do a lot of documentation which can be used later on for quality tracking purposes, for process improvement purposes. They actually command several units in a very coordinated fashion, such that best volume and quality of production can be reached. So, they coordinate individual groups of machines and they give them appropriate set points, so that you get products of a certain quality and of a certain volume. And they also handle plant emergencies, shutdowns, failures, accidents, etc. So, they actually manage the production process. Below that you have the actual automatic control, in this case referred to as unit control, and below that you have the field level where you do sensing and data acquisition. Since we have done this in detail, I am not going to spend time on this. So, this is a picture which shows that typically in a process control situation, not a discrete manufacturing scenario, the kinds of technologies that are used. So, you have and also the time scales that I was talking about. So, you have at the bottom level you have these sensing, actuation, protection, alarm systems, which typically work at sub 1 seconds kind of time scales. Then you have the what they call regulatory control, or which we call automatic control. So, this is kind of level 0. Then some of it is actually level 1, and then this, as we said, that you need to give very good set points to these automatic PID loops. So, that is again computed by multivariable control models, where you consider the interaction among the various variables. You do what is known as model predictive control. Is a very modern technology which is used for using number of process plants. So, here you are talking about giving set points which hold for typically for over minutes, hours kind of horizons, and then you have real time optimizations, where real time optimization is also done at the level of multivariable and constraint control. So, you have real time optimizations for actually for various kinds of, excuse me, I have to switch off my mobile phone. So, and then finally, on top of that you have the planning and scheduling modules, which again, as I said, that decides what is to be made and typically work on days, months, weeks kind of time frames. So, this is a diagram which shows the various kinds of technologies that are used. For example, for planning scheduling, you have to do demand forecasting, you have to do supply chain, you have to, if you want to know that what sort of what should be a schedule, then you have to know what kind of orders are going to come, what is your inventory, what time does it take to actually procure raw material from the market. So, that is supply chain management, raw materials and product planning and scheduling. So, at these various stages you use different kinds of techniques, and there are very advanced software tools today available which actually help plant managers take these decisions. So, so we come to So, now we start talking about the various levels, and we start with from level 2. So, level 2 is supervisory control. So, the major functions of supervisory control are the following. So, you have first of all optimal set point computation. So, when you are supervisory control is typically concerned about a group, one machine or a group of machines, and they have to be their operations will have to be coordinated. So, you have to give them optimal set points, so that they can achieve the performance goals of the production. Like typically, let us say a supervision system will, let us say they if you take a steel plant, then you have a blast furnace feeding to the steel melting shop or the basic oxygen furnace, and then basic oxygen furnace feeding to the continuous caster. So, you need to give set points to all of these. For example, the continuous caster will have a set point given to it of the casting speed, that is at the speed at which the slab is going to come out of the caster. Now, obviously, that is going to be decided based on the kind of molten steel supply situation, right. So, the molten steel supply situation depends on the basic oxygen furnace. So, you see that these set points, firstly the continuous caster casting speed specification has to be given based on some, there are some other considerations also, like for example, that there is a phenomenon called breakout, where if you do not give the proper cooling set point, cooling system control and the proper casting speed, then sometimes molten metal can actually come out of the slab, and then you have to stop production, and there is a lot of problems, right. So, there are other technical considerations, but there are also considerations related to coordination among the different units. So, all this is done by the supervisory control layer. Similarly, one has to supervisory control always looks at the process and sees whether things are going fine. For example, breakout detection, as I was saying, that whether by looking at the temperature profile, by looking at the mold levels, whether it is possible to the system is always monitored such that whether we can detect the possibility of a breakout and then immediately take corrective action, so that breakout does not occur. So, that would be like process monitoring. Similarly, if process reconfiguration and tuning, sometimes it happens that you need to retune your controllers because the process slowly changes, or because there may be some problems with the raw material quality, or there may be some problem with some power source, like let us say the pressure source may have a low pressure problem. So, in such cases sometimes you may have to retune your controller such that it gives optimal performance in terms of quality, efficiency, energy efficiency, etc. So, the direct result of monitoring is reconfiguration and tuning as and when necessary. Similarly, sometimes this is done, all this is done manually. So, if it is to be done by operators, then the operator has to be given a very good insight about the things that are happening in the plant, which may be quite far away from the control room. So, there is a process visualization system, man machine interfaces which have to be provided. And similarly, process event management. So, I mean something trips, some alarm goes, some pressure level shoots up. One has to activate strategies, shutdown mechanisms, emergency mechanisms, such that the situation is managed with the least amount of production loss, with safety and reliability to the personnel and the equipment. So, such things are typically handled at level 2, or these are the functions of the supervisory control. So, essentially when you are giving a set point, there is an element of optimization involved in this. So, that is shown here, that this is your automatic control loop. So, this is your automatic control system, this is your set point, this is the set point, and this is your system, closed loop system. So, you always try to find out that. So, first of all you get the data from the process and you actually reconciliate it, that is you they may contain noise, some sensor may be they may be inconsistent because of various reasons. So, first you, before taking decisions, you reconciliate the data, that all the signals make sense according to standard mass balance, energy balance equations of the process. So, once you do that, then you have got good data, good and valid data. Now, based on that you may like to compute various kinds of performance indicators of the process. What is the production volume, what is the deviation from quality, what is the for example, say what is the magnitude of the control input, that what is the input energy that have been consumed, what is the agility of the plant, what is the dynamics, that if there is a set point change, what is the process variability. So, various things, various features of process operation can be computed, and based on that you get an idea as to whether your process is working fine, or whether it needs a new set of new set points, that is another cycle of real time optimization will have to be done to generate new set points. So, this is typically the way in which the supervisory system is always looking at the plant and then carrying out optimizations based on set points. Now, these optimizations can be done in various ways, and finally, you want to minimize cost of production, and cost of production generally per unit, and you as we have talked about in our first beginning slide, that if you want to make more profit, then I have to cut down on the cost and I have to increase the production. Now, increasing production how far? So, that can be limited by typically by two kinds of things. Firstly, there are quality constraints. You cannot produce things too fast, because then they are going to, they may not be of adequate quality. Then there may be production volume constraints, that you cannot, you do not know how much, even if you can meet the quality constraint, how much you can produce can actually depend on your equipment capacity, how many it can actually produce, or it can be restricted by the market, because you do not want to produce things which won't sell, right. So, so typically if you go to a I mean, this is what I always find, that if you go to a sweetmeat shop or some food shop around 9 o'clock in the evening, you will find that many of the items have been finished. So, they actually schedule their production in such a manner that towards the end of the day it gets exhausted. So, I mean, they will not produce more, because food is a perishable item, and they don't want to produce more than they can sell. So, sometimes volume of production can be also constrained by the market. Similarly, where you have very energy intensive processes, or where energy is the main bottleneck, like in a let us say an aluminum refining plant. Say an aluminum refining plant actually works on electrolytic principles, and it is highly energy guzzling, and it works on electric energy. So, it is that way a very clean plant, where literally hundreds of thousands of amperes actually flow through those aluminum pots. And these here I mean, in such a plant, production is can sometimes be actually limited by energy, because it may be because that amount of electrical energy, some of it typically aluminum plants have their captive generations, but sometimes they may also draw power from the grid, and in which case especially in developing countries like ours, there may be constraints on that. So, in such a case energy consumption will be a very critical optimization criterion for giving set points. So, similarly, minimizing waste through effluents. So, that can be, again it can be, for example, you typically optimize fuel air ratio to save calorific value of unburnt hydrocarbon. You do not want carbon monoxide to actually escape into the atmosphere, because that can be burnt further, and you are actually, if you are escaping carbon monoxide, then you are actually losing calorific value of the fuel that you are using. That is number one. Number two is that sometimes you may be restricted by environmental considerations, like you cannot dump acidic or basic effluents into rivers, right.